All right. Good morning, those on the American time. Good afternoon, those on the Moscow time, whatever your time of day. So today we will continue with. I should have left some space here for the title. So we'll continue with. Let me turn off this chime. So we continue with the elliptic or stable envelopes for simplistic reductions. Maybe I'll denote it like that. And applications. And so what's this about? So this is a brief summary of what we discussed in the previous lecture. So what's a symplectic reduction? You have a symplectic manifold, a smooth symplectic algebraic symplectic manifold with a symplectic action over group G. And then the symplectic reduction is, by definition, you take the zero locus of the moment map, but take a GIT quotient of that, which in our situation where stable equals semi-stable is that you take, so then you take the stable locus of in the zero locus in the zero set. In the zero locus of the moment map, the closed set, you take as open set, which is stable locus, and we also assume. So in our case, this action, in fact, this action on the stable locus is, so in the assumption that goes here is that stable equals semi-stable, and then in fact, no finite stabilizers. So this is either an interesting top project to consider whether I can let go of either of this, but that's what happens for Nakajima variety. So let's just go with that assumption, and then so this means you have if we denote the zero, the preimage of the zero set of the moment map we denoted by Y, and the ambient space we denoted by Z. There's the same diagram behind me. Then we have this kind of diamonds of inclusions. So there is the stable part in Z, and there's the ambient space. There's a stable part. There's a zero locus of the moment map, and there's a stable part. And then when we take the first thing we do is we take, so what's a stable envelope of a class? If I have a class alpha here, so here I have class alpha here. So then I lift it, then I pull it back to the stable locus. So pull back here. And then in principle, I could have asked the question, maybe I can extend it to, so this extension here from the stable to the whole thing, that is problematic because somehow this is an open inclusion, and I can ask whether I can extend the class from this open set to the whole ambient space. Maybe this could be problematic since Y is not smooth. In this sort of extension arguments we use, there is some smoothness that plays a certain role. So let's not do that. So instead we push forward here. And then we would like to extend this. Now here is extend so that, and then extend so that it supports that it is supported on Y. That clear? So we go, somehow we go this sort of route. These are easy operations, and then this is the interesting operation. This term here. Let me draw a more. Let me make a better kind of graphic thing. So is this part, is this last turn, which is interesting. There's a pullback and push forward. There's nothing to it. And so then, in what sense is it like the stable envelope before? It's the stable envelope, like the stable. So there are two answers to that. So like so similarities, maybe like the abelian stable envelope we discussed before. So this kind of non-abelian stable envelope solves an interpolation problem. Why is this? Why is this an interpolation problem? It's because if I consider the inclusion of an open, stable inclusion to this is then the opposite map in cohomology would be typically so in our case would be typically the opposite map would be or maybe the corresponding map in cohomology would be in fact a closed embedding. So this, if I take the elliptic cohomology of Z stable, that would be, so this one is open, but this is a closed embedding. Right, so this is embedding of the kind like when we remember we had this for projective space. For projective space, this elliptic homology is something like, it's like elliptic homology is some sort of union of abelian varieties, and then this you embed into the ambient. So maybe I'll draw a picture. So there's some union of abelian subvariety. This you map into the ambient space. So these are sit-ins. Right. So this is think about the projective space, things like big picture like that. So means to extend. So we're asking it's a question we ask to extend a section of a line bundle from a closed set to the whole thing. This is like finding a section that takes given values at given points. It's an interpolation problem. And so if you ask for sections of line bundle to extend this interpolation problem, that's clear. Also, so it means we interpolate here to the ambient space. I remind you that the notion L that stands for the spectrum means the elliptic homology class are functions or sections of a line bundle on that spectrum. And so if I have a closed inclusion of spectra, then that means I'm asking to find a section that interpolates given values at a given subscheme. That's clear. And also must vanish under, so you take Z minus Y, so it has to be supported on Y, so it has to, if you take the open inclusion, Z minus Y, this is again open inside Z, Right? But similarly, if I take elliptic homology of this open, the exact same thing. So elliptic homology of z minus y, this would be closed. So it means that this is my ambient thing, and then there's some other thing which I maybe draw some other way it's enclosed, and then it has to vanish there. And so these are typically, so what are these things concretely? This means when it's not satisfied by restrict to the zero locus satisfying the moment map equation, that has to vanish. And then this is typically, so if you look at what this is as an example, these conditions are what's called the will conditions. Right, so what's an example of that? An example of that is, so for instance, when it takes for help C2n, the Z after all, this is like home V 2 copies, and then plus V dual, right? And then there's a moment map. This is where the operators. So that you have a GLN acting there, and maybe we denote an element in GLN. So we're talking about GL equivalent elliptic homology, elliptic or K theory or something. So we need some notation for x1, xn, and then there is these two copies here have weights. So maybe let me make it more explicit. Let me make two copies like this. Let me put a multiplicity space here. So multiplicity space would be C, or maybe I'll just write some variable T1 plus T2, and then this V dual would have the weight T1, T2, something like that. And then it's an exercise to check that the condition that when it has to restrict to zero outside of the zero moment of the moment map. This will condition says, and whenever I have the situation when maybe mnemonically, or maybe I first write the answer and I'll write the mnemonics, is that when it has to be if among the x's xi, xj, xk, if that set is equal to C, CT1, CT1, C2, or C, CT2, CT1, C2, then it has to be, so then it has to be zero. So in other words, this is the union, this sort of thing, that is the union of this. And mnemonically, you should think of this as being a situation when you have a box of 3 boxes like this, or 3 boxes like that. Then these are the contents. So in other words, not only you have to interpolate some values. You have to interpolate the interpolation problem in the sense that you solve 2 problems. You have to interpolate something interesting from the set you care about, and also you have to vanish. You have to continue to vanish where you're supposed to vanish. Right? You see in the literature, you might see these will conditions. The meaning of the will conditions is that it's some vanishing condition for things on the stack, and the meaning of that vanishing condition is that you restrict to the complement of the moment map, to 0 level of the moment map, and then the homology class has to vanish there. That's the instance of that. And so this is in one sense so in one way so this was number 1. says it's an interpolation problem. Second, number 2 is that it may be solved inductively using stratification of the unstable locus discussed last time. Yeah, so again, abelian stable envelope is some way to extend the homology class, means it's an interpolation problem. And we solved it by some induction on the strata. Similarly, there is a similar kind of stratification, a kind of a slightly more complicated inductive stratification for the unstable locus, which we need to extend this across the unstable locus. And this we discussed last time. This is the stratification, which generalizes, has as good properties and generalizes what we've seen in the abelian cases, kind of attracting manifolds and so on and so forth. Right. And then I didn't say what is it from the beginning. I didn't say what is it we're interpolating. So maybe we should so then maybe takes values. So we're interpolating section of some line bundles, and maybe we'll say where it takes values in some line bundle S or some sheaf S, but maybe first define S naught. Maybe so that it's actually a line bundle. And what is that line bundle? If you think about this diagram here, so here you had a section. Here you had a section of, so maybe in some different color, in red. So here we're doing theta of polarization of X tensor something of degree 0. Usual thing. Then we pull it back. When we pull back a class, and nothing changes. And then when we push forward, then we have to the tangent space changes. So then the push forward. Here in this push forward, I get the theta function of the normal bundle, which is what? Which is the theta of from well, I mean, exactly normal bundle has this weight h bar inverse times g dual. That's where the moment map lives. Moment map takes values here. So when you take the normal bundle, you get additional thing here. And so in the end, when you get so you get here, if you put these 2 and 2 together, you see that you're getting something which is a polarization of Z, which makes sense that is symplectic times degree 0. So then takes values. So just like the abelian envelope, takes values in S naught, which is the polarization of Z times something of degree 0. So this is the line bundle, and maybe more specifically, you may want to consider a sheaf which already solves the will condition. Means you take S, which is the kernel. You take S and restrict it to kernel of restriction to Z minus Y. So this is, in other words, you impose the will condition. This is a line bundle. If you make a section vanish at some point, this is more like slightly more different, more general shift, but it's okay somehow. You interpolate either. So it's a question of right. And so then maybe to remind ourselves, what does it mean degree zero? So this the most interesting thing from degree zero, this degree zero, the most interesting part of that, I mean, most interesting for us, this comes mean source. Mean source are, well, you can say G current line bundles on Z, but especially just characters, especially line bundles of the form of Z times a character. Maybe call that character chi. And then if you think of those, of elliptic functions in sort of kind of usual way, so this means, what does it? So then if I take this, we like this line bundle, maybe call it ULZ. So that is of that a section is kind of, so this is a section with a section, of which a section. So Z is this variable. Those are the Kähler variables, or maybe dual Kähler variable. Has the section of the form theta of. So if this is my bundle, then the section would be just theta chi here. So that would be, that's my L. So then I take theta of chi of x times. So this is an element. X for my coordinates, chi of x is a function, theta of chi of x maybe z. Well, it depends on your convention, that maybe plus minus it. It depends on the convention. Let's put z here. And then theta chi of x. Theta of z. This sort of thing. Okay. Maybe 2. And if you remember, so we discussed this formula for the Grassmannian. Formula for the Grassmannian is that this there in the Grassmannian, this part manifests itself. There is a product of theta x I z something in the Grassmannian. In the Grassmannian case, if you get to get the determinant, so this would be this is like that, and then this cancels, and the corresponding part. So then the corresponding denominator, we should think xi times whatever, this part, and then there's a theta of z. And this part here, that cancels. Polarization. So this means we don't need the we get something regular, so there's no denominators here. So this is 4, and then point number 4 is that if G is in fact like an academic variety product of GLBI, all right, then the corresponding, then this GIT stable envelopes reduced, which I explained is the way really reduced to abelian loss. So this is, I'll explain if I have time today, I'll explain how that goes. So hopefully I'll have time today, also maybe later. Okay, so this is to comparison with what we've seen before. Now, as to the applications, so let me look at my notes here. Right, so the main applications, so as I said, so this is number one. Maybe hopefully next time, if I get there, maybe hopefully next time. I hope next time. Next time, I hope, is that this says that if I take this vertex with descendant, this really, so if I think of this as a map, so this is a map from K-theory of X. So if you read about the correspondence between K-theory of X, and then that goes to the K-theory of the stack, this object is equals to elliptic stable envelope times some gamma factors, which I'll write like that. So this is. But then today we will instead. So today we will talk about the relations between the capped guy. We relate this. Kind of. This is the capped vertex to descendant, something we discussed maybe 2 lectures ago, a while ago. And so this is we relate. Okay. We relate this. This is capped. So something more to the key thread stable level for the stack. So this K theoretic means this means Q goes to 0 limit. Theoretic. This means that Q goes to 0, and then log Z over log Q goes to something. This corresponds. This determines the slope. Maybe we won't be too precise. And so what's the statement? The statement is that if I take, so let alpha be a class in the K theory, current K theory of X, and then I take the stop of alpha. So this is in the current K theory of the ambient stack. Maybe cross G. And then what would I like to do? So then I'd like to consider, so then there's a following theorem. And this is in this beta paper with Mina. It says the following. It says, so this is, I remind you that this is supported on mu equals 0. So then what I will do is I'll take this stop alpha and I divide it by maybe I'll write it like that. This is the weight. And I explain what this means to divide two classes. What's concretely, so if I have for GLN, this weight would be, so for GLN, this would be a product where I now take in R and J, all of them. This 1 minus H bar times Xi over Xj. These are the weights of the joint representation, and this is H bar because that has weight H bar. So, and if I stick this into relative here, then this is the same if I just stick alpha into the tube. So that's, so we had the other, this was somehow, we had another way to, we had this kind of, we have this map going the other way. We had a formula, this kind of, this really goes opposite way. From Smirnov form. In a way. So here Smirnov says how to compute. Well, Smirnov says something else. I mean, it says something else. It says there are some specific descendant insertions that if I stick them, then I get inside the relative insertion. And now I have to explain what this means. Division. Well, division means we here. So what does it mean to divide? This is here we take the map. The map here. Here we study maps. That satisfy moment map equation, right? And so somehow this means F maps. Okay, we have maps F from our P1 to X to maybe Z to Z, such that mu of F of T that is identical to 0. And then, but now we put a class. So F of 0, that's the evaluation. And this means for the evaluation, we already put a class that satisfies the moment map equation. So there's really no need to put other constraints. It means we can take instead, we can take, yeah, put the prime here. So you take the stop of alpha. And what does it prime mean? Prime means that we take all derivatives, dk, need the partial, take straight derivatives, dk dt to the k of mu f of t. We want all of them to be 0 starting with k equals 1. But we don't impose the condition at the value, because the value, this takes care. This takes care of mu of f of 0 being 0, right? Because the class already supported there. You don't need to impose this condition. Does that make sense? So there's, in other words, if you write localization, suppose you write localization formula, Then this means in local, so means, in other words, means this denominator, this cancels with the corresponding numerator in localization formula. This is English what this means, because in localization formula there will be a weight of the moment map since you impose the moment map equation, and so then there will be always that weight of the moment map, and that weight of the moment map you're free to take out because you already impose a class which is already supported where you want it to be supported. That makes sense? So now the statement is that these two things are equal, and then the corollary that in any geometry whatsoever, so in any integral whatsoever, suppose some kind of integral here, and then I have a relative insertion. So if I put the relative insertion, call it alpha, that is always equal to the same integral where instead of the relative insertion, I put now descendant insertion. Well, I mean, so that I don't know how to put the primes here. So, well, maybe I'll just write stub alpha over h bar, or you can take all the primes, or with the primes. I mean, primes is just an explanation what this means to put this insertion. So, okay. So these are just universally equal, and what's the proof? So proof is just, as usual, just bubble it off. And so if I have a point, I can take that point, I can bubble it off. So that would be then whatever I had before. So I'm not going to draw a general curve now anymore. So I had a point when I can say, so we put this point at the end. This is always equal to, I take the same thing. And then I take, let me move it a little bit here. And then I can not so good. Can bubble it off means I put the relative condition here, and this comes. There's a glue matrix here, so I don't have to remind you. So then this is now P1. You can take any curve with a point, it can degenerate to P1 glued at that same point. So here's the gluing. And point, this is the P1 with 1 point relative and 1 point whatever. And so for P1, on this P1 we apply the theorem, here we apply the theorem. Incidentally, if you're worried about what is it, how does this argument work in families, suppose I have a family of curves. So these are the kind of these are the kinds of issues of this sort of cohomological field theories. Today in the seminar will be a talk about cohomological field theories by none other than Rahul Padanipandi himself. So I really recommend you listen to that. Anyway, so anyway, that's the proof. And so then another corollary then corollary square is that I can apply it to, so for instance, I can apply it if I take relative and now I take a non-singular condition. So I put whatever alpha and beta here, classes, that by this argument, by the decided proof, this is the same as I take stop alpha over delta h bar times this, right? This is just a special case of what's above. But now this object here, this is a vertex which is relative at one point and it's non-singular at the other point. So this is a fundamental solution of our difference equations. On the other hand, what's this? This I claim this thing I can write as an integral over kind of, maybe I'll write dx over x products. And then there will be stub alpha of x divided by this product of 1 minus h bar xi xj. And then there's a product of q gamma over q gamma. Over some cycle which I denote beta. And this is what I was saying before, is that really in this formula here, there will be some, this part here, there'll be some cancellation between them. Okay, that may be something. But why is that? This is because the fixed loci, so if I take on this moduli space, so mind you that this is computed by localization, so there's an action of Q, and so fixed loci on this moduli space are themselves quotients, JT quotients by G. And if I integrate, if I want to know, I want to compute the Euler characteristic of some pre-quotient, we call it Y, maybe not Y, some pre-quotient, call it maybe call it Q, because that's a pre-quotient on G, some sheaf, which is some sheaf F. So maybe suppose I have F. So this is a G covariant sheaf on some space Q, or maybe some space, maybe curly Z, something like that. And then I'd like to know the Euler characteristic of, if I take the quotient Z by G, and I take the induced sheaf. So the induced shift on the quotient means that I take the invariance. So what's it going to be? This is going to be, I take the Euler characteristic on the pre-quotient. And then I take the invariance, just by definition. This means what it means to have a shift on the quotient, the sections on the quotient. Maybe I'll write it like that. So the sections on the quotient are the invariance of the stuff upstairs. And then this I can express. This is an integral over maximal torus in G by well integration formula. And then if I'd like to compute now with some stability condition, maybe there's a character of that involved. And then I compute f of G. Well, that would be the same thing, but now with a contour. That depends on the stability condition, the same thing, integrate the same thing. And why is that? Is because by definition, this means this is analytically continued. This is value at m equals 0 of things like, take the Euler characteristic of L on the actual quotient, and then you take f twisted by some large power of the character, take G invariance, where m is very, very large. So this would be analytic for m large number. This will be analytic in m. And then you stick m equals 0 in that formula, and then if you do analytic continuation of integrals, means here means here. This means you have to do steepest descent here. So maximal torus, maximal compact torus, sorry. So instead of generating, so there's some real cycle which you generate, but now you have an integral, which is you have to analytically continue in m. How do you do that? You use steepest descent, and then this means you change the contour, and then this contour will reflect, the steepest descent will reflect on the change of here. So maybe a reference for this is the appendix. It's not exactly new material. This is well-known material, but maybe it's in a convenient appendix to this paper with Mina and Edik. So anyway, this formula gives me the conclusion. Then the fundamental solution of our K-difference equation so it's some matrix, has some parameters alpha and beta, or maybe I'll take the fundamental solution and I kind of take it matrix elements alpha beta. That's an integral of over some cycle that depends on beta. then this would be then you take the step alpha, then some product over gamma gamma, then dx over x. This sort of thing. Okay.
Sorry, can you, can you go back a little bit?
Sure. Like how far back?
Well, a bit more to the previous theorem. In the proof, I would just. So you say apply the theorem. Apply which theorem?
So I said it's a theorem that this is a theorem which I'll hope to explain today. And then, so this theorem implies that not only in this particular situation we have an equivalence of insertions, but in any other situation we have equivalence of insertions. In particular, when the point at infinity is non-singular, then that's also a possibility. And so then, so we get to that formula.
And then after this, there was this section of. So I didn't quite catch how you reached this conclusion, but so this is a derivation here.
This is from the theorem which I didn't prove. It's a derivation, yes.
Oh. I mean the conclusion that's in your paper with Frankel and Mina.
No, in the paper with Frankel, we just explained that it's very generally if I have. I mean, it's not a new fact that if I have some kind of JIT quotient, then an integral over the JIT quotient, that the other characteristic of something on the JIT quotient is an integral. On the cycle, it depends on the stability condition. That's so the statement is it's not. This is not a. This is not a new. Like I said, this is not a new theorem in math, but I just don't know a convenience reference.
Sure, I'm just trying to understand the logic. So I think maybe can you move down a little bit? That towards.
Why don't I just make it smaller and then we can.
Oh.
You can see the logic. So.
So this corollary. Okay, that's fine.
There's the corollary square. So the corollary square says the fundamental solution is equal to the same integral with instead of relative point you take the descendant. You take descendant point, and then the integral on this geometric integral on descendant with this map descendant point that actually some actual integral, like Riemann integral, and which.
I see. I guess I missed why you started talking about the Euler characteristic of a sheaf.
But it's what we're computing in K theory. K theory is you compute. So what does it mean to compute in K theory? It means you compute the Euler characteristic of some sheaf on some modular space. But your modular space is a quotient. So just saying the modular space is itself. So means maybe let me stress this point. So these are the. So. Modular spaces of the subjects. So take this and take now the fixed locus of that. So this is maybe it's not a surprising point, an important point. These are JT quotients by G. So when we integrate over the modular space, means we can integrate over some JT quotient by the group G, means that there will be some integral. What that integral is, you have to compute. I mean, it's not maybe I'm not going to explain that, but the fact that there is an integral.
Okay. So.
Okay. So we have a formula now. And so now in this formula, we can take the limit q goes to 0. So maybe I should go back. So this is to this point here. So it's maybe not, it's not a major point, but let's but maybe I'll stress this here. So here we have so maybe it's here. So maybe the point I want to make. So this would be compare and contrast with Smirnov's formula. So now maybe on the contrast side there is no there's no z and no q in stop alpha, because right now this is k theoretic. In this discussion, this is a k theoretic stable envelope, has no z and has no q, because q has been set to 0 and z's been killed also. And so this is the expression where Smirnov's formula says, I give you an assertion, and then I can compute it in terms of some other stuff I know we previously know, but that will involve z and q, obviously. But here I say the opposite. I say there's something which is no z, no q. I stick it in the vertex with descendant, and out comes something we previously know anyway. So so that's anyway. This thing has no z and no q, so I can, when I take q to 0, I'm not worried about this part at all. There's nothing happening with this part. So this is k theoretic. Let me remind you that this is k theoretic. In particular, there's no q. Whereas, of course, this thing will blow up as, the exponential of, sorry, not q to 0, q to 1. This will blow up as some function. Maybe I'll call it, some kind of w of x and other stuff divided by. This will blow up as a exponential of some function. W of x and other things divided by log q. So if I take a q gamma function, let q go to 1, it's going to blow up. Because that would be, infinitely. You take infinitely. If you get, q gamma function is an infinite product. If you go q to 1, then instead you're going to get some, well, you can do that exercise. And so then what was the conclusion? The conclusion that this integral, the saddle point in this integral is where that the derivatives in x, partial dxi of function w equals 0. And this is where the integral will, will sit. On the other hand, so if I have a solution of a q difference equation, so if I'm solving an equation of the form psi q whatever qz, let's say equals, in some variable, let's say z, qz, there's some matrix m of zq applied to this psi z, then if I get q to 1, my psi will be, I get solutions of the form, get asymptotic, this asymptotic will be of the form, so first I have to get an eigenvalue of this matrix, so psi I, q to 1, I keep taking q to 1. So this vector psi better be eigenvector. of the matrix M Z1, and then there will be something like exponential of like integral of the eigenvalue. This is the eigenvalue. Sorry, the 1 over log Q integral lambda I. This is the thing where this is the eigenvalue. And so then if we compare these formulas here and there, we see that this tells you what the spectrum is. So this this expression here, well, that's the beta equations in some different color. And this is the point. This is in some sense the point which is very, very closely connects to the original thinking of Nekrasov and Tashadashvili. So maybe I'll write their names here. Of course, there should be they you know, if I'm not their spokesperson, I can't talk for them, but my understanding is that they wrote the integral of this kind, and then an integral of this. I mean, they took something like an integral. Suppose I take you get an integral even if you take just that. So it means this means take the descendant vertex with the class 1 here. So there'll still be an integral, so you don't worry about the insertion stop, which we worry about it now, but it's still integral. The saddle point of the integral, you see that in examples, it gives you beta equations. And so this tells you that the spectrum is going to give by the beta equation for which they made, for which their insight was that in fact the whole structure should be that of a quantum group integrable system, which is correct, which is what we were doing in this class. And so this is the fact that this, and then the other conclusion is that then the function stab alpha, what is that? Stab alpha, that's the off-shell beta eigenfunction. What is by definition off-shell beta eigenfunction, or what you stick in the beta ansatz? What does it mean? It means beta ansatz means what's the word? You hypothesize the form of the solution, and then the form of the eigenvector you hypothesize, and then it turns out to be a true eigenvector if certain equations are satisfied. And so this is then your hypothetical form. So in traditional beta ansatz, this hypothetical form, so this is i.e. the well, maybe I'll just keep it all shoved letter. So this ansatz is what it is the ansatz. Right? This is what you try. It's the there. Ansatz. That's not how I'll spell ansatz. It spells. So this is so what you substitute and see if it's an eigenvector or not. So that's the stable envelope. And then if the beta equation are satisfied, then it's then you get the actual eigenvector. Make sense? And maybe I'll say it one more time. So then Z in this discussion, so Z is a parameter. So similar to quasi-periodic boundary condition in spin chains. And then when z equals 0, then I mean this is a very strange limit to take from the point of view of spin chains, but it's okay thing to take for Hamburg. This is the corresponds to this quantum integral system. This becomes just classical multiplication. In case here of x, and this is the spectrum well, just the spectrum of a current K theory of x. So this is one of, these are the things which we draw all the time. So the spectra of all the things that look like that. So maybe I'll draw a better picture. So like for projective space, this would be, the really, or for the Hilbert scheme of points, these are the things which are these are components determined by fixed points. And fixed points of the torus action, this would give you eigenvectors or generalized. So if you have for example, if you have isolated fixed points would be so fixed points. So classes. So if I have a P in X, if I take the torus fixed, then so then the OP is a class in a current K theory of X, and that is an eigenvector. Because if I take any sheaf whatsoever and I tensor it with OP, that's just the fiber of P tensor OP, right? So this says this is an eigenvector of anything, and so these are then there's the fixed points are this is the spectrum, and if the fixed points are not isolated, then there's some thickness to that. There's some kind of some Jordan blocks. If fixed points are not isolated. So that's the spectrum. And then if I now turn this deformation with z is not equal 0, then this picture will deform into some interesting equation. So let's say maybe something like that. So let's say this line it was double, and so maybe it looks like that, and that sort of thing. So so that would be so these are this deformed scheme. These are the beta equations. And then on the whole space, I have some on the whole space I have my classes, the stable envelopes, and when they're restricted to the beta equations, I take stable envelopes. Restrict the beta equations, then I get the eigenvector. Okay.
So is it true that this spec of K, from the integrable system point of view, is just a graph of eigenvalues? Can I think of it corresponds to a graph of eigenvalues in the integrable system, or
it's a spectrum of a ring. You have a commutative ring.
Sure,
Or
sure,
integrable, quantum integrable system is a commutative ring. It has a spectrum, and the spectrum of a covariant K-theory, that's something we understand really well. These are the and it looks like that. And this is, I mean, this means that if you're covariant, you take a maximal torus in your group, you take all the fixed loci. So this would be the component, and then well, in general, if you can have also some other components. But anyway, the components correspond to fixed points of various subgroups. So that's in general. But if you're flat over your covariant variables, then you have the fixed point of a maximal torus. That's all you need. And then each component will correspond. Each component may or may not be a point. If it's not a point, it's a Jordan block. If it is a point, well, it's a point.
Yeah, I'm asking, like, in integrable system, you can consider like just all the eigenvalues and then see how they change as you change parameters.
Yeah, that's exactly what's happening.
Okay.
Exactly, yeah.
All right. Mm-hmm. And
So
also,
I mean, you have some commutative rings, and they're so these commutative rings depending on the parameter. And I'm asking you, what's the corresponding? This would be commutative ring depending on parameter means you just have a ring and some commutative ring and some more variables, and then you can ask fibers of the corresponding spectra over different values of z, and this would be at z equals 0, you get the classical K theory, and it's something we understand. And it's z equals not 0, then you get the beta equation, which is some deformations. Some interesting algebraic variety, some interesting to study.
Also,
So
sorry,
yeah.
One more. In this last statement that it gives you eigenvectors, so it assumes that the stab itself is the off-shell Bethe eigenstate.
No, we've proven that. We've proven it. We've proven it.
Okay.
Because we've proven more general thing. We said that this something solves. So if you know how to solve the non-stationary problem with an integral, then in particular you can diagonalize the stationary problem. We solved the more general problem. So this is something was understood long time ago. It's when shortly after Reshetikhin and the other Frankel wrote down the QKZ, then Reshetikhin was asking himself how to solve the QKZ. Well, this grew into a very, very big industry solving the QKZ by integrals, but somehow in the very, very old papers of Reshetikhin, you can say, well, since this is a problem. This problem generalizes beta ansatz. Maybe what we should integrate is the off-shell beta function. So this is the fact that this was later, of course, was used by this kind of argument was used by many people. But in any case, the solving a Q-difference equation by an integral is a problem which is strictly more general than diagonalizing the value at Q equals 1 of the equation. Because there's just a stationary phase in the integral. Okay. So now I have maybe 15 minutes to actually prove the theorem. So maybe 15 minutes. I'm not going to prove it in every detail, but maybe I'll argue. I'm not gonna. So there is something I was planning to do today, and you can see the pictures of that at the top of the page, which I guess we're not gonna do it. But so why don't I give the proof and then we have a general discussion of the so I'm going back. The theorem. This is a paper of Min and I. So maybe I'll write it like that, so that you don't see it just mine. So what the theorem says is if I take this step alpha, this is this object, this is the K theoretic. And so this K theoretic at the case takes an input, takes a slope plus polarization. And this needs to be fixed. Correctly. And so then this is over this. Take this. This is supposed to equal to, just take alpha. Right. So this reminds us of this. So this was after all. This is the tube which we proved is the glue. Remember, this is the tube equals the glue from earlier lectures. And then so then in that earlier lecture, one of the proof that tube equal to glue was based on the fact that this does not depend on Q. And what was the argument there? One of the arguments there is that tube equals glue. That was the argument when we prove that something is a Laurent polynomial in Q, and then we let the Q go to 0, go to infinity, and computed that in fact it's constant in either limit, so it is a constant. And so then we'll do the same here. So first of all, that this is by localization, this part. By localization. What would localization look like? Localization would look like that. So then you take this step over that thing, and then you take a non-singular condition at infinity. So this means there is just here there's just will be some edge terminal localization. And then maybe some different color here, like that. And so, so then what is this in reality? I remind you this in reality. This means in reality that means you have all these bubbles opening up. And so in particular, if when we localize, there will be there is the class of the form. When we go back to this tube equals glue type computation, there will be this 1 over 1 minus Q times psi. And so what we expect, and what is the same, the proof from glue, saying the same proof as in the glue equals tube theorem. We of course we conclude that this whole object here, it goes to the glue matrix as Q goes to 0 and goes to 1 as Q goes to infinity. Because if Q goes to infinity, then you think that this denominator is suppressed, and you'll be right. But there is also a case when the accordion doesn't open at all, and so then it'll just be 1. Okay. And so then we need to show. So about this, we have to show. Here we have to show that this goes to, so the limit we want, when this goes to just alpha, just alpha as q goes to 0 and something bounded as q goes to infinity. Right. So this is means we have some integral, and this is a proper integral. So this integral here, this integral is proper. This object is proper. So around polynomial q. And then we would like to show it's equal something, and so then it's enough to show that it's equal to something if something we want in q equals 0 limit, and it stays bounded as q goes to infinity limit. Then it will show that first of all it's constant, and second it's equal to what we want because it's equal that in the q equals 0 limit. And so that means we have to show we take this vertex with this descendant, and then it has to show that it satisfies these conditions. And this is the crux of the argument. And then that's again of a typical. This is like a typical rigidity proof. So, as I say almost in every single lecture here, a rigidity argument, the way it works is that you prove something is around polynomial. That is usually not so hard. And then you have to actually sit down and estimate the weight. And then, so this is not an exception. With one has to, from the definition, so from the definition of stable envelopes, we know that the weight satisfies some bounds, and then we have to use these bounds to conclude this, because these are the things we need to compute. And so then, so that you sit down, you do that, or you read in the paper, and that's how the argument goes. So this is left. I mean, there's no point me doing this estimates here in class. Right. So I still, maybe as a preview, like since we so preview. Since I have a few moments and I have preview of what of we have above, we had this had the statement here. Here's this statement. Now, what's it going to be like? What's it going to be like for the Hilbert scheme of points? So let's just do it for x equals Hilb C to n. We need to produce alpha cohomology class. We need to get a symmetric function. Of n variables of x1, x2. Xn. And what we will do, we'll find it as a, so we need a map from a cohomology class, a map to symmetric function. That's the stable envelope. So how that's supposed to go? So then we take, we will find it as an element We will find it. As a matrix element. Of the R matrix. Between what and what? So the R matrix in, you take the matrix in help. I'm not gonna write homology, I just write it as is, and then kind of cross. And now we take shifts of rank n. And so this is, so you take like n, this is like, this corresponds to kind of like n copies of the defining representation with x1 through xn being related to playing the role of what we normally call A1 through AN in GLW n-dimensional space, framing variables. Right? So maybe so this is like saying if this is a Fock representation, this is the Fock space, Fock representation of R elliptic or Q or whatever quantum group. So stable envelopes have different flavors. Similarly, quantum groups have different flavors. So if you take that, so this corresponds to like the tensor product of this Fock representation, each evaluated its own xi. So which matrix element we're going to take? We're going to take the matrix element that I want here. So maybe. So this is my Fock space here. And here I take the tensor product of from I goes from 1 to n of Fock spaces evaluated xi. Then here get my class, maybe take a partition of n. Here's n is equal to 4 in this example. So I take a partition of 4, have 4 boxes. I take a vacuum on the other side. So there's nothing. So there's the vacuum here on the other side. On this side, there's vacuum. And then I take the matrix element with some specific guy. So I take kind of K boxes here. So, and then each is a box at the origin. Each is at the origin. The origin means x and y are both 0. The multiplication by x and y are both 0 maps. And then xi's are kind of, xi's sort of like record, like the height and then in well, right. It's like the coordinates of these boxes is some extra direction. These are the x1, x4. Think about it, what this thing records. Right. So instead of kind of instantons of some fixed rank, you all this. I mean, of course, you can do it for not just for the Hilbert scheme of points. You can do it for instantons of any given rank, and then instead of your instantons were here on top of each other, but then you let them all be just a zero size instanton, each own framing, its own, and the framing variables are kind of like the distances in some other directions. Because framing variables are like, the way I'm saying is that if you think about how you form the contents are the contents of the box are like have to do with 3 coordinates, or right, and so then this, if you take on each layer it gets all multiplies over its own xi, and so then this means you have some other direction which xi's are the coordinates. I mean, if you think in terms of coordinates, here are the coordinates. Here my contents are of the form 1, maybe T1 inverse, whatever. Let's say T1. Strictly speaking, T1 inverse, but on the other hand, depends on the stability condition. All right, this T1, T2 square, this sort of thing. And here, this contents are just x1, x2, x3, x4. Right, so you take this matrix element as a function, and that function is and then my claim is that is the stable envelope. This is function 1. This matrix element. Is nullability stable. Okay, proof next time. Questions about anything I said today or before?
So at the beginning, there was this application where if we had non-singular and arbitrary points, that was going to be equal to the stable envelope. Is this today in the relative descent correspondence supposed to be a consequence of that, or is this some kind of unrelated statement?
I don't know how to relate it. I don't know how to see it from Smirnov's formulas. I was trying to say so. This seems like it goes in kind of the opposite direction, and it has, generally speaking, different flavor. So it seems like it's well. Also, this seems like an easier thing to prove. I gave you more or less a complete proof of that, whereas this type of Smirnov's formula, I mean, it took us a while to. Well, I didn't prove there are many things I didn't prove there. The proofs exist, but I just didn't pretend them.
But so this number 1 though, that of these, can you go up a tiny bit?
Yeah, sure. This one?
Yeah.
Yeah. Oh, at that time, no. This is something else entirely. Yeah, this I don't know how to reduce to either statement. Yeah, this is about the full vertex with descendants, and so then actually, that of course depends on Q. So it has to depend on Q. And then I claim if you take out the Q gamma dependence, then it'll be elliptic stable. Yeah, this is the kept vertex. That has very minor dependence on Q. So I mean, essentially independent on Q. I mean, it does depend on Q because it depends on what you. There's, so to speak, kept vertex with descendants is still a finite by infinite matrix, and of course you can, in this infinite part you can stick many other things, and then of course you'll seeing some Q dependence. But what we've proven today is that some kind of essential part of this matrix. There's some interesting part of that matrix is in fact Q independent.
Another question. So
Sure.
today you contrasted this GIT stable envelope with abelian stable envelope. And does it make sense to consider something for a equivariant theory, or whatever, K theory or elliptic, with a non-abelian group? Or, I mean, I guess there are no fixed points under non-abelian, but the
so this general statement, the general non-abelian statement is you can make a very similar statement without the moment map without, but that would be so there's you can say, you can ask for well, maybe let me say it like that. So if you define a non-abelian stable envelope with some sort of extension from the stable locus to the whole thing, that you can say it like that, then everything we considered falls into that category. Right? So the things we consider for the abelian group and for non-abelian group, they both can be phrased if you extend something from the stable to the whole
thing. Another thing. So I didn't quite catch. Did you prove that that K-theoretic stable envelope gives the off-shell Bethe eigen off-shell Bethe state?
Well, to the extent we prove anything in this course, I did prove it, yes. Because
can you
so maybe I'll remind.
that?
Yeah, okay. Well, let's review the logic of that. So so this is the theorem which I kind of explained how the proof goes. That's the theorem. From this theorem, you conclude that if instead I take the non-singular condition at infinity, that the equality is still true. Right? Then about where you have a matrix where one side is relative, the other is non-singular, then that we know is a fundamental solution of Q-difference equations.
Okay.
And on the other hand, the other side, that's some integral, where the stable envelope is just the integrand. I mean, integral in the sense that we had some fancy integrals in some Korean cohomology theories, but this is like a Riemann integral in which the stable envelope. So stable envelope is some K theory class on the stack, which sounds profound, but in the end, it just means it's a symmetric function of some variables. And so then this means in this integral, that symmetric function will appear as an integrand. Okay. So that is established. Now, since we have established, so this establishes this. So if you take the fundamental solution of your difference equations given by an integral, but then in particular, if you know how to solve your difference equation by an integral, then in particular you know what are the eigenvectors and eigenvalues of the limit q to 1 of your matrix. Just because that is the steepest descent of the corresponding integral. And what's the steepest descent in the corresponding integral? There's some q gammas that is going to blow up, and then the integrand, which is stable envelope, which is stands there because it's independent of q. And so then it says that says what? I mean, dependent on q, also independent of z. It's just something which just stands there. And so then what's the statement is that the saddle point in this integral is given. You have to look at the critical locus of the part that blows up, and on that critical locus you evaluate the integral, which is to say that to find the eigenvector of some matrix, you take some ansatz given by the stable envelope, has some parameters xi, and those you have to substitute. Those you have to stick to some solution of some equations. The solutions of equations are the critical points of some integral. And then you can it's an interesting question of what is it, whether it's an interesting question of whether we need all critical points or just those critical points that deform correctly to z to 0. So that's an interesting question. One means this kind of but we know that everything, for us, it's the answer is that the critical point is So the critical points we need are the ones that correctly deform the z to 0. So that's another. So there's in principle there's some in principle there's some analysis of this critical set needs to be done, but like I said, since we have a deformation, since we have one point at which we understand everything, then means we only select those solutions that correctly deform z to 0. But presumably they're all, but maybe there's some others that I didn't investigate. It's an interesting question. That's an interesting question to investigate.
Mhm. I see. So is it correct that you find that stub alpha is a device such that if you insert solution of a Bethe equation, you get the eigenvector of the left hand side, and that's how you conclude that it's an off-shell Bethe?
Right. This is by definition what's off-shell beta eigen function. So by definition, off-shell beta eigenfunction is some such thing that if you stick on the solution of beta equation, you get the eigenvector. Of course, this is maybe not so not such a great characterization because it's not clear this thing is unique. But certainly, if maybe if you think about this logic, maybe a better characterization is that if your off-shell beta eigenfunction is whatever you need to integrate to get the solution of the non-stationary equation. So maybe that's a better definition.
I see. Because I was expecting something like raising operator, say in the Yangian acting on the vacuum or something like that.
But this is, if you think about this, this is, if you think about this, this is, what's that? What's the picture here? It's some particular. So this means you create.
Mhm.
I mean, this is this is to be contrasted with. If you think about what this, so maybe next time we'll explain next time. So this is this object here is like an algebraic beta ansatz type of reformulation. So if I've really applied, so this means I've created my I can create my state by some operator. I mean, you can read either side of that. So you can read either side of that as an operator, but
okay.
That's the, if you think what's, if you, I mean, it's a good example. Think about what it says for exercise. Recast T**-Grassmannian in the same form. So this is for in the same form, you should get like B of x1, B of x2. Think on the vacuum. Oh, that will be that. It's a good thing to think about. Why is something like this is a generalization of all the classical forms?
Okay, thanks.
Sure.
One more thing. What's the reason that there's always this interplay between k-theoretic and elliptic stable envelopes going on here in this, like, yeah. Like sometimes
I'm not sure. I don't think I can answer that question. I mean, so in general, so maybe I say it like that. So this is, we deal here with in this kind of counting of the maps, we deal with two objects, one which look like difference equations themselves, and the other look like the solutions of the difference equations. So generally speaking, if we have a Q difference equation, that is something defined in the world of K theory, and then and so then means I mean, this is, you think that this is where K theoretic stable envelopes are relevant. But when you take about, you have so maybe stepping back also to cohomology. So if you're in cohomology, then there's a quantum difference equation and the quantum differential equation. Quantum differential equation is phrased in terms of kind of Yangian cohomology. In other words, the cohomology theory related to additive groups. However, if you write it, if you'd like it solutions, solutions will more look like objects that have to come with K-theory. Similarly, it's more this becomes even more pronounced in this situation here when we write equations and other things that's related to equations, things which tend to be rational functions in Z, tend to, have no or little dependence on Q, and so then those objects have to do with them. Those objects, like if you take the QKZ itself on Q, it depends in a minimal way. It's just a shift by Q. Nothing else depends on Q. So this is these objects are K-theoretic objects, and they then the K-theoretic envelopes are relevant. On the other hand, if you look at solutions of Q difference equations, or maybe the monodromy of solutions of Q difference equations and so forth. This have to do, so the solution of equation. What means a solution of equation? Solution of equation means it's some sheaf on solutions of Q difference equations. You can multiply by functions which are Q periodic. Means this is a sheaf on an elliptic curve or on some abelian variety. Means solution of Q difference equation, the monodromy, and so on and so forth. This is explained now in terms of elliptic theory. And so in general, if you have some passage from equations to solutions or from equations to their monodromy, is always the passage from the additive group to multiplicative or from the multiplicative to elliptic. That helps.
Thank you. Yeah. I've also sent something on the channel if you could take a look. But
sure.
Yeah. Thank you.
Maybe not right away. So we should all get a little bit of rest, maybe have lunch or dinner or whatever time of the day, because in 40 minutes or so I anticipate to be a very interesting talk by my very good friend Rahul Pandripande in the seminar, and so I hope you all can join, and I'll see you there. But then for this lecture course, that's all we have for this week. So then I'll see you next week.
Are they streamed anywhere, by the way?
What?
These other seminars that you
you just go to the webpage of the seminar. It's you can find it from my webpage.
Oh,
Sure.